When we talk about rotational dynamics, we have to begin with torque. And what torque is the measure of the twist produced by a force around a particular axis that may be located anywhere. Torque, we also know this as the moment of the force about a particular point. And the way to calculate torque is it's the product of the force and the moment arm. And we're going to get into what we mean by moment arm. If we look at a door and we push on a door, it's going to rotate about an axis. Okay, now we can direct our force perpendicular to the door and see this as a top view of the door. So here's the top of the door and here's the hinges. It's going to rotate about the hinges right here. And the perpendicular distance from that axis rotation to the force is our moment arm. And most times you'll see this R with a little perpendicular symbol. This is our moment arm. Moment arm. And again, our torque, represented by the tau symbol, is equal to our force multiplied by our moment arm. And this is really easy to do when the force and the moment arm are perpendicular. However, life is not always quite that simple. So sometimes when we have an axis of rotation, let's say the red dot is our axis of rotation, and let's pretend we've got a door. This is the object we're acting on, and our green line is the force. Okay, the door is what we're acting on. So let's define this as r vector. Our moment arm has to be perpendicular to the force. So what does that look like? And how would we figure that out? And how do we know that's perpendicular? Because if we extended this force down, we could see that's perpendicular. Now this force makes an angle with the object we're acting on. Makes an angle here, theta. And that angle is also equivalent to this angle. So, what does this all mean? If we're going to look at this trigonometrically, what could we say about the perpendicular or moment arm in terms of this r vector? We could say that moment arm is equal to r times sine of theta, because sine of theta, sine is opposite over hypotenuse, okay? And if this is the perpendicular here, this is our hypotenuse, r over hypotenuse. So our torque in this instance is equal to the force times the moment arm. The moment arm is defined by r sine theta. So the torque is equal to r sine theta. And we got to know what this angle is that this force is acting at. Another way to think about this is in terms of our force. You can also think of our torque in terms of it's got to be the perpendicular force that's acting on the object, the radius of the object, between the action of rotation. So this perpendicular force How can we define that in terms of our F? Well, that perpendicular force is equal to F times sine of theta. And if we want to specifically talk about the perpendicular force, its moment arm is this radius. Its moment arm is this radius. So the torque in that instance would be equal to radius times F sine of theta times the perpendicular force. And it turns out that these two are the exact same equation. Force times radius times sine of theta. So we have an easy way to figure out the torque based on, it doesn't matter what path this force is taking, if we're pulling on the door this way, if we're pulling on it this way. If we know the angle that it's making, that the force is making from the x-axis, we can say the torque is R, is force, whatever the force is, times the radius, times whatever the, let's say, the length of the object we're acting on, times the sine of theta. And if we look back at our object here, this was the same equation because the angle that the force is making is 90 degrees, and we could say that this is still sine of theta. But if we did sine of 90, sine of 90 is equal to 1 times everything. So we get the special case for when we have a perpendicular force where our formula is just the torque equals the force times the moment arm when the force is perpendicular, where the moment arm is equal to the length of the object we're acting on.